Today we're looking at the K-Pure Math Unit 2 2019 exam. So let us begin. Question 1. Let 4x squared plus 3xy squared plus 7x plus 3y equal to 0. Use implicit differentiation to show that dy by dx is equal to that expression they have there. So let's differentiate. So differentiate 4x squared. So differentiating this equation here, 4x squared, we end up with 8x. And to differentiate 3xy squared, we're applying the product rule. So we are going to treat the 3x as a function and the y squared as a function by itself. So differentiate 3x, we end up with 3. We keep in the y squared. Plus, we're alternating now. So we keep in the 3x. Differentiate the y squared using the chain rule. We end up with 2y dy by dx. Plus differentiate 7x, we end up with 7. Differentiate 3, we end up with 3 dy by dx equal to 0. So I want to group all the terms with dy by dx. So we have this term, which is 6xy dy over dx. And we have plus 3 dy over dx. We're going to group everything else on the other side. So we have minus 8x. We have also minus 3y squared. And we also have minus 7. Alright. So let's factor dy by dx from these terms. So we end up with 6xy plus 3. On the right hand side, notice we can divide each term by minus 1. So we can factor minus 1. And we end up with 8x plus 3y squared plus 7. And then we divide both sides by whatever we have in the bracket. So we divide both sides here by 6xy plus 3. Divide by 6xy plus 3. So we end up with dy by dx. So that answer that is 1. Equal to, and of course we have minus. So here we have 8x plus 3y squared plus 7. And of course in the denominator we can factor out 3. So we factor out 3. So we end up with 3 into itself is 1. And 3 into 6xy, that's 2xy. So we did the proof as we were asked to do. Next. So part 2 deals with partial derivatives. So the function here is f xy equal 4x squared plus 3xy squared plus 7x plus 3y. So it's obviously it's a proof. So there are some things we need to find. Let's find partial f by partial x first. So when we're doing this differentiation, we're treating the y as a constant. So differentiate 4x squared, we end up with 8x. Differentiate 3xy squared, remember we're treating the y as a constant. So we end up with just 3y squared. And differentiating 7x, we end up with 7. Differentiate 3y. 3y is a constant, so that will become 0. Let's also get the second derivative. partial square f, and we'll get this by differentiating partial f partial x with respect to x again. So this 8x becomes 8. 3y squared, we're treating the y as a constant. So we get 0, differentiate 7, it's also 0. Now let's get partial f by partial y. So this time we're differentiating the function with respect to y. So we're going to treat the x as a constant. So differentiate 4x squared, we get 0. Differentiate 3xy squared, we get 6xy. Differentiate 7x, we get 0. Differentiate 3y, we get 3. Let's do the second derivative also with respect to y. So differentiate. So again, we're treating x as a constant. So differentiating 6xy, we get 6x. Differentiate positive 3, we end up with 0. Now we also need this expression, that one there. So this would be partial square f upon partial y partial x, and we'll get this expression by differentiating partial y, this with respect to x. So when differentiating this, we're going to treat the y as a constant, so that means we'll end up with just 6y, and differentiate 3, we get 0. Now to do the proof, we're asked to show that the 6 partial f by partial y minus 10 is equal to all we have here on the right hand side. So let's work out the left hand side first and then right hand side after, and see if we have the same thing. So the left hand side of what we're trying to prove is equal to this. So it's 6 partial f partial y minus 10. So it's 6 partial f upon partial y minus 10. And we have partial f by partial y, that's 6xy plus 3. So that's 6 times 6xy plus 3. And we have minus 10. If we expand, we end up with 6 times 6xy, that's 36xy. 6 times 3, that's 18. 18 minus 10, that's 8. So the left hand side is 36xy plus 8. And the right hand side, so the right hand side is, let's check. The right hand side of the proof is partial, the second derivative, partial square f, partial y square, partial square f, partial y square. What else we have? Times partial square f, partial y, partial x, partial square f, partial y, partial x, and then what else? Minus the second derivative, partial square f, partial x square. Partial square f, partial x square. So, alright. So when we simplify this, we should end up with 36xy plus 8. Now, partial square f, partial y square, that's 6x, so that's 6x times partial square f, partial y, partial x, that's 6y, minus partial square f, partial x square, that's this, that's 6x. Sorry, partial square f, partial x square, that's 8. It's 8. Actually, the proof says plus 8. So it's plus 8. So plus 8. So notice the left hand side. Notice the left hand side is equal to the right hand side, abbreviating RAH for right hand side. Therefore, this proof was quite easily done. Let us move on to part B. Use De Moivre's theorem to prove that sine 5x is equal to all of that there on the right hand side. So based on what we have here, De Moivre's theorem says cos 5x plus I sine 5x is equal to sin x, cos x plus I sin x raised to the power of 5. So the De Moivre's theorem says that if we raise a complex number in its polar form to the power, we can just multiply the power there by the angle there, right? So the 5x, 5 cos 5x sin 5x. So let's expand the right hand side. Now notice the right hand side binomial expansion there. So to get the coefficients, we can use small numbers there. So we can use Pascal's triangle. So yes, 1, 1, 1, 2, 1, 1, 3, 3, 1, 1, 4, 6, 4, 1, and for the coefficients for the fifth is 1, 5, 10, 10, 5, 1. For the expansion, we use these coefficients. Alright, so we would have 1 times cos x to the power 5 I sin x to the power 0 plus cos x to the power 4. So as this power is falling, the other one is increasing. So I sin x power 1 plus cos x power 3 I sin x square plus cos x to the power 2 I sin x to the power 3. And let me just put in the coefficient same time. So for the second one, the coefficient would be 5. It's 5. Let me just change it. Well, put in everything and then put in the coefficients. Alright, so the final one, the cell, not the final, second to last, cos x to the power 1 I sin x to the power 4 plus cos x to the power 0 I sin x to the power 5. Let me just put in the coefficients now. Use a different color to put in the coefficients. So the first one is 1, 1, and 5, then 10, and 10 again, and 5, then 1. So the values in the red, they represent the coefficients, the coefficient of each term. We're going to multiply that to the term. Alright? Let's move on to the next step. Now, bear in mind, you really want to prove sine 5x. Notice sine 5x represent the coefficient of the imaginary term, the I. Alright, so let's just, so you really just want those coefficients. So therefore sine 5x, and of course we're going to equating the coefficients of the I. of the I, the imaginary part, right? So you only, so sine 5x, that's what we're trying to prove. So we only want the I coefficients, all right? So let's do that now. So here, this is I sine x to the power 0. This will be, which is 1. So we won't need in this term. We won't need in the first term. So all right, we won't need in the first term. The second term, of course, here is I sine x. So the second term would be cos to the power 4. So cos to the power 4 times I sine x. So times sine x. We're not repeating the I. So we're leaving the I, just the coefficients we're putting there. Alright, so we're done with the second term. For the third term, would I actually have I square? Now, I square is minus 1. So the third term would end up be a real term. The next term, I cube. So I cube is actually I square times I is actually minus I. So I just give us a minus I there, so it's a minus term. And of course we have the cos square. We have cos square x. And of course we have a sine cube times minus I, but of course we're not putting down the I. Next term would have I to the power 4. Now I to the power 4 is 1, so that would not give us an imaginary term. Next term is cos x to the power 0, I to the power 5. Now I to the power 5 is I to the power 4 times I, which is actually 1I, which is actually I. So this term will be a term in I. Of course, cos x to the power 0, that's 1. So we'll just have sine to the power 5x. Alright? So we need to show that everything we have on the right hand side here is equal to what we have on the right hand side there in the proof. And then remember to put the coefficients. So for the cos 4, there's a coefficient there is 5. Alright, for the term with the cos square, the coefficient here is 10. So it's a 10. So actually times minus 10 here. That's for this term with the cos square. And the final, the coefficient here would be 1. So just 1 times that, which is that, alright? Let's continue. Now you will notice that what we're asked to prove, on the right hand side, all of the terms are in sine. So we need to convert all of the cos terms to sine. So 5 cos to the power 4, that's cos square x times cos square x. And then we have sine x minus 10. And we know cos square is 1 minus sine square. So 10, and I'm put the sine cube here first. So it's 10 sine cube x. And then cos square, that's 1 minus sine square x. Plus sine to the 5th power x. Alright, so we know cos square is 1 minus sine square. So cos square times cos square, that's 1 minus sine square x times itself. Alright, so cos square times cos square, that's 1 minus sine square x times itself. And we have sine x outside. And here we can distribute this minus 10 to each term in the bracket. So we end up with minus 10 sine cube x plus 10 sine to the 4th power x plus sine to the 5th power x. Continuing. So here we actually have 5 sine x outside. So 5 sine x. Let's expand the bracket. 1 minus sine square x squared. So we can square the first term. Minus 2 times the product of what we have in the bracket there. And square sine square with sine to the 4th power x. Good. And then here we have everything. So we have minus 10 sine cube x. We just repeat these. Plus 10 sine to the 4th power x plus sine to the 5th power x. Alright, let us expand. So 5 sine x times each term in the bracket. So we head up with 5 sine x, and 5 sine x times that, that's minus 10 sine cube x, and 5 sine x times that, that's 5 sine to the 5th power x minus everything else again. So minus 10 sine cube x plus 10 sine to the 4th power x plus sine to the 5th power x. Let's just group the like terms we have in now. Now an error was made up here when we're distributing a negative 10. Negative 10 times negative sine square. It's at the powers is actually sine to the 5th power. 3 and 2, that's 5, right? So this should be sine to the 5th power, negative 10 times that's 10 sine to the positive 10 to the 5th power. Alright, just read it here. So it's 10 sine to the 5th power. Sine to the 5th power. So this should sine to the 5th power, right? Alright, so we're grouping sine to the 5th power. So we have 5 and 10 and 1. So that's 16 sine to the 5th power x. Now to the 3rd power. So we have that. That's minus 20 sine to the 3rd power, and then this is 5 sine x, so 5 sine x. Is this our proof? 16 sine to the 5th power minus 20 sine to the 3rd power plus 5 sine x. Alright, so that's the proof. That's it. So sine 5x is equal to that expression there on the right hand side. Alright, so the proof is done. Let's move on. Right, the complex number z equal negative 1 plus root 3i to the power of 7 in the form r equal I theta, where r is the modulus of z and theta is the argument of z. So r is root the real part square, which is 1 or minus 1 square, plus the imaginary part square, which is root 3 all square. So r would be square root of 1 plus 3, that's the square root of 4, which is 2. Let's get theta. Theta would be equal to, before the theta, let me actually do a sketch. Imaginary axis, real axis. So theta, the real value is minus 1 and the imaginary is root 3. So it would be in this second quadrant. Alright, so this is the angle that we want. So let me call this theta. Now the calculator will give me the primary angle here, alpha. So using the calculator here, alpha, let me find alpha first. So alpha would be tan inverse root 3 over 1, which is 60 degrees, or pi over 3 radians. So this would be 60. Hence theta, therefore theta would be 120 minus 60 degrees, which is 180, sorry, which is 60 degrees, 180. Angles on a straight line, add to 180. So 180 minus the 60 degrees here, which would be 120 degrees. And if we multiply 120 by pi over 180, we end up with 2 pi over 3 radians. So that's theta. So in the form r equal ri theta, so therefore the complex number z is equal to r, which is 2, e to the I theta. So I times 2 pi over 3. Alright. Next. Hence prove that -1. Alright, so just realize we're asked now to raise it to the power 7. So therefore, if I raise both sides to the power 7, alright, so z to the power 7 is equal to 2 to the power 7 is 128. So 2 to the power 7 is 128. So I reach the 2 to the power 7 and the e term to the power 7. So 7 times 2 pi over 3, that's what? 14 pi over 3 times I. Next, we're asked to prove that -1 plus root 3i to the pi over 7 is equal to that. So remember that -1 plus root 3i to the power 7 was equal to 128 e to the 14 pi over 3. 14 pi over 3 I. So we can put this in the polar form, the r cos theta form. So we can write this in the polar form. R is 128. In the bracket we'll have cos 14 pi over 3 plus I sine 14 pi over 3. And this we can use our calculator to determine. So we have 128 outside. Let's work out cos 14 pi over 3. So cos 14 pi over 3, that's -half. Remember, when you're using pi, put your calculator in the radians. And sine 14 pi over 3 is root 3 over 2. So it's root 3 over 2 times I. So I can now distribute the 128. What are we trying to distribute the 128? Or maybe, so distribute the 128. So we'll end up with -64 plus 64 root 3 times I. Of course, we can factor out 64. So in the bracket, we'll have -1 plus root 3 I. Same as what we're asked to prove. For question 2 is an integration by parts problem. So I'll be using integration by parts. Now, let me just, the rule I will be using. So the integral of uv dx. Alright, so I'm going to call this 1. I'm going to rewrite, so I'm going to rewrite f n x equal integral of 1 times ln x to the power of n dx. So the 1 I'll refer to as u, and the ln x to the power of n I'll refer to as v. Just move this. Okay, so the rule I'll be using as so first will v times the integral of u minus, I have a large integration sign there, differentiate v and put back the integral of u dx. Alright, so matching this, u are going to integrate 1, integrate the u 1, I get x, and I put back the v, which is ln x to the power of n minus, and then large integral sign there. I put v prime. Now what we have at v? We have ln x to the power of n as v. So I'm going to differentiate this. So u, I'm using the u as 1 and the v as ln x to the power of n. So v prime, I differentiate ln x to the power n using chain rule. So chain rule, it would be n times ln x. I subtract 1 from the power, differentiate ln x, I get 1 over x. Alright, so that's the v prime. That's the v prime I just wrote down there. And then the integral of u. And of course the integral of u was x, right? So times x dx. So 1 over x times x, that will cancel. So we end up with x ln x over n minus the integral. Can move this now. Minus the integral of n. Let me put of n ln x all to the power of n minus 1 dx. So this would be equal to x ln x raised to the power of n minus n. N is a constant there, so I can put the n. And if you look at what this is, log x to the n minus 1 is f subscript n minus 1. Alright, of x. So therefore, proven. Hence show that f subscript 3 2 minus f subscript 3 to the of 1 is equal to the expression here we have on the right hand side. So let's find this expression first. F subscript 3 of 2. So we go back to fn. Notice fn, where is it? Here it is x log x. Let me just repeat it. Let me just rewrite it down in there, so I don't have to keep going up and back and forth. So let me just rewrite it. Alright? So this, I replace the n with 3 and the x with 2. So I replace x with 2 and n with 3, right? So 3 minus 1, that's 2. I replace x with 2, so I end up with that. Now, so of course, we're going to need f subscript 2 2. So f subscript 2 2 would be equal to, at this time I'm replacing both the n and the x with 2. So 2 log 2 to the power of 2 minus 2 f subscript 1 of 2. Which means we are also going to need f subscript 1 of 2. So f subscript 1 of 2 will be equal to, this time I'm replacing the n with 1 and x with 2. So x with 2, so 2 log 2, replacing n with 1, minus, replace n with 1, so minus 1 f subscript 0 of, and replacing x with 2, right? So f0, let's look at what f0 is. So f0, let's look at what f was again. Here's what f was. So f0, if you notice, f0 of x will be the integral of log x to the power of 0, replacing n with 0, dx. And we know anything to the power 0, any non-zero term to the power 0 is 1. So it's the integral of 1 dx, which is equal to x. So f0 x would be x. Alright, so f0 x would be x. So f0 would be x. So let's work out f3 too now. So therefore this would be 2 log 2 minus x, and of course we can put this into, so this means that, let's work out f2 again. So this means that f subscript 2 of 2 will be 2 ln 2 square minus 2 times f12, which is f12 is 2 ln 2 minus x. So this would be, so f22 would be 2 ln 2 square, expand, I would get 4 log 2 minus 10 plus 2x. And then to get f subscript 32, f subscript 32 is equal to 2 ln 2 cube minus 3 times what we have here for f22, and f22 we have to be 2 ln 2 square minus 4 log 2 plus 2x. So f subscript 32 would be equal to 2 ln 2 cube, expand the bracket here, so we'll have minus 6 ln 2 square plus 12, distribute a negative 3, plus 12 ln 2 minus 6x. So this should be ln 2 square. To complete the proof, we also need an expression now for f subscript 31. So f subscript 31 this time we are going to replace the n with 1 and the x with 3. So 3 ln 3 to the power 1. No, so it's replacing n with 3 and x with 1. So we'd have 1 ln 1 to the power of 3. So 1 ln 1 to the power of 3 minus, and then here, remember we're replacing the n with 3 and the x with 1. So it's 3f21. So now we need to find 3f21 or f21. So common f, right? So f2 subscript 1. So we're replacing the n now with 2 and the x with 1. So replace the n with 2 and the x with 1. So it's 1 log 1 square. 1 log 1 square minus 2 f11. So 2 f1 1. And of course now we need to find f11. So f11, this time we're replacing both the x. We're replacing both the x and n with 1. So again, so it's 1 log 1 1 minus 1 f0. 1 minus 1 f0 1. And remember, we already found f0 to be x. Remember that f0 was x. So this would be equal to, and log 1 is 0. Log 1 is 0. So it's minus, and f0 was x. So it's minus x. As a matter of fact, all of this will be 0. Well, log 1 is 0. That's a 0. That's 0. That's 0. So this f2, f subscript 2 1 will be negative 2 times f1. Now remember, f1 is negative x. So f subscript 2 1 will be negative 2 times f11. So negative 2 times negative x. That's positive 2x. And therefore, f subscript 3 1, notice is negative 3 times f21. So it's negative 3 times f21, which is 2x. So it's times 2x. So it's negative 6x. And we're replacing the x with 1 in the bracket here. So that's just negative 6. So it means therefore, what we're asked to prove now, it means therefore, we're asked to prove that to do an expression for f32 minus f31. So f32, so f subscript 32 minus f subscript 3 1, f subscript 3 1 is equal to whatever we have for f subscript 3 2, and we have it here, f subscript 3 2, here it is, 2 log x 2 log 2 cube, here it is, minus 6 log 2 all square plus 12 log 2 minus 6x. Let's subtract now. Subtract now f31, which is 6. So I'm just write it down here for quality, so we can all see. So f subscript 3 of 2 minus f subscript 3 of 1 is 2 log 2 all cube minus 6 log 2 all square plus 12 log 2, and for here we are subtracting f31, which is negative 6, so it's minus 6, right? So this will be so and then 6x for f of 2, so this 6x would actually be 6 times 2, that's negative 12, so that will be negative 12. So over here with negative 12, so we're substituting the 2. So negative 12 plus 6, that's minus 6. Alright, so that's f subscript 3 of 2 minus f subscript 3 of 1. Should give us this expression there. Let's check if that's what we have. So here, that's what we're asked to prove. Alright, and we'll end up with the same expression. 2 log 2 all cube minus 6 log 2 all square plus 12 log 2 minus 6. Alright, so part B, we can let y square plus 2y plus 1 over y to the 4th power. No, this just is you should recognize that what we have in the denominator here is actually y square plus 1 times itself. So y square plus 1 all square. It's important to recognize that. So let that be equal to a over y square plus 1 plus by over y square plus 1 all square. So it's all about rewriting this as y square plus 1 times itself. So we're continuing. So y square plus 2y plus 1 over y square plus 1 all square. So this term, we can, to get the y square plus, to get the same denominator, so y square plus 1. So multiply denominator by y square plus 1 to get y square plus 1, same as here, y square plus 1 all square. And we'll do the same thing to the numerator. So the whole idea of equivalent fractions plus, and the second fraction is already y square plus 1 all square. So we can drop all the denominators now and so we have y square plus 2y plus 1 is equal to a into y square plus 1 plus by. We can expand the bracket, so we end up with ay square plus a plus by. So we can equate coefficients of like terms. So notice for the y square term, a is equal to 1. And for the term in y, the coefficient of the y there is 2 on the left hand side and b on the right hand side. So b is equal to 2. So therefore the proof is done. So this replacing a with 1, so therefore the expression here is proven. So a would be 1, b would be 2. Alright, so proven. Hence or otherwise evaluate. So you'll recall that this expression was equal to, just rewrite it, was equal to 1 over y square plus 1 plus 2y over y square plus 1 all square. For this one we can just dy. For this one we can just do integration using inverse trig function. So a would be 1 there, right? So that's 1 over a, so 1 over 1 tan inverse y plus, and the other one we can use integration by recognition, reverse chain rule. So plus, let me just rewrite this. So this is 2y into y square plus 1. Law indices, this become negative 2 dy. So of course we can use a reverse chain rule here. So tan inverse 1, tan inverse y plus, and so the reverse chain rule, or by recognition, y square plus 1. So we add 1 to the power there, we get minus 1, and we divide in by minus 1. And if you should differentiate this, what you'll actually get is 2y. You'll get negative 1, y squared plus 1 to the minus 2, multiplied by the bracket, multiplied by the bracket differentiated is 2y. So it's integration by recognition, plus a constant here. And of course, using indices one more, we can rewrite this as minus 1 over y squared plus 1 to the power 1, which is just y squared plus 1, plus our constant. Let's move to question 3. Determine the coefficient of the term in x cubed in the binomial expansion of 3x plus 2 to the power of 5. So we're doing the expansion 3x plus 2 to the power of 5. So we only want the term in x cubed. Let's look at the coefficients for the using Pascal triangle will be 1, 1, 1, 2, 1, 1, 3, 3, 1, 1, 4, 6, 4, 1, and the fifth power 1, 5, 10, 10, 5, 1. So the would be so x3x to the 4th 1, 5, 1, 5, right? So 3x to the 5th, 3x to the 4th, 3x to the 3rd. So it will be actually the third term when the coefficient is 10. So it will actually be the third term. So when the coefficient would be 10, that's the third term. So we have 10 3x to the power of 3, and it will be 20. So coefficient is 1080. So part B, show that the binomial expansion 1 plus x to the power of a quarter plus 1 minus x to the power of a quarter up to the term in x squared is, alright, so let's determine what's 1 plus x to the power of a quarter, 1 plus x to the power of a quarter, and we're going to use the formula 1 plus nx plus n into n minus 1 x squared over 2 factorial. So we're stopping at the term in x squared. Right, so in this case, n would be the power, which is a quarter. Alright, so it would be 1 plus a quarter x plus n is a quarter, so quarter into quarter minus 1 upon 2 factorial, which is 2 times x squared. So this will be 1 plus a quarter x, and then a quarter minus 1, that's minus 3 quarter. Minus 3 quarter times a quarter, that's minus 3 over 16, divided by 2, so that's minus 3 over 32. Minus 3 over 32 x squared. Let's do the same for 1 minus x to the power of a quarter using the same formula. It's equal to 1 plus nx. So it's actually, we use a negative x now. So it's negative a quarter x plus n, which is a quarter, into a quarter minus 1, and of course times this, we remember, is now negative x, so negative x squared, all over 2 factorial, and we'll end up with 1 minus a quarter x, and the same third term, because negative x and x squared give us the same thing, so we end up with the same negative 3 over 32. X squared. So we add, so therefore 1 plus x to the power of a quarter plus 1 minus x to the power of a quarter, so we can add the like terms. If we add the constants, we get 1 plus 1, that's 2, and then quarter x plus negative a quarter x, that's 0, and then minus 3 over 32 x squared, minus 3 over 32 x squared, that's minus 6 over 32 x squared, that's minus 6 over 32 x squared. And of course you can always reduce the minus 6 over 32 to divide by 2, you get minus 3 over 16. Let's continue. Hence, by letting x equal to 116, compute an approximation for root 17 plus root 17 plus root 15, the fourth root, correct to 4 decimal places. Alright, so we're going to replace, so from here, continue, we're going to replace x with 1 over 16. So in the bracket we have 1 plus 1 over 16, fourth root, plus 1 minus 1 over 16, fourth root, equal to 2 minus, well, 6 over 32, we're going to write it as 3 over 16, times x squared, and x is 116, so 1/16 all square. Okay, so now this is what, 17 over 16, so this is 17 over 16, and of course the fourth root. This is 1 minus 1/16, that's 15 over 16, fourth root, equal to 2 minus, let's calculate what we have on the right hand side here now. Well, the entire right hand side works out to be 1 point, just 1 go in a calculator, 1.99993. Alright, so let's go back to the left hand side. So we can take the fourth root of each of numerator and denominator, so the fourth root of 17 and the fourth root of 16, that's 2. We can do the same thing, the fourth root of 15, and again the fourth root of 16 is 2, equal to 1.9993, 4 decimal places. And of course I can times both sides by 2. If I times both sides by 2, I end up with the fourth root of 17 plus the fourth root of 15 equal to 1.9993 times 2. I'm getting 3.9985. 3.9985, which is what we're asked to do, the summation of the fourth root of 17 and the fourth root of 15. Let's move on. Part C, the function h is defined as x cubed plus x minus 1, defined on the interval 0, 1. Show that h of x equals 0 has a root on the interval 0, 1. So let's find h of 0. So h of 0 would be 0 cubed plus 0 minus 1. And let's find h of 1. h of 1 will be 1 cubed plus 1 minus 1, which is positive 1. So notice h of 0 times h of 1 is equal to minus 1 times 1, which is minus 1. That's less than 0. So therefore, by the intermediate value theorem, so by the intermediate value theorem, a root lies on the interval 0, 1. In other words, a root lies between 0 and 1. Next, uses iteration x subscript n plus 1 over 1 x square subscript n plus 1 with initial estimate points 0.7 to estimate the root h of x equals 0 correct to 2 decimal places. So we have x1, let's begin with x2. So if we are using x2 now, we're letting the n be 1. If we let the n be 1, what we actually have is 1 over x square sub 1 plus 1. And we just found this to be, well, we are told it's 0.7. So 1 over 0.7 square plus 1 will be equal to 0.6711. So let's do about share 4. So x subscript 3. This time we're letting the n be 2. Right, so it's 1 over x square plus 1, subscript 2 there, is 1 over, and we just found x subscript 2 to be 0.6711 square plus 1, and that will give us 0.6895. Let's write with 4 decimal places since we want 2. Let's find x subscript 4. X subscript 4. This time we're letting the n be 3, so we'd have 1 over x square subsect 3 plus 1 equal 1 over 0.6895 square plus 1. That will give us 0.6852. So we're getting closer to the true root every time. Let's do one more. So 1 over, this time we're letting the n be 4 plus 1. So it's 1 over 0.6852 square plus 1 equal to 0.685. I think we have done enough. Okay, we'll do one more. Let's do one last one. So now we're letting the n be 5 plus 1. So that's 1 over 0.685 square plus 1. We end up with 0.68 to 2 decimal places. I will start there. So the root is, so 2 decimal places. So root is 0.68 to 2 decimal places. Let's continue. Part D. Use the Newton-Raphson method with initial estimate of x subscript 1 equal to 5.5 to approximate the root of g of x equals sin 3x in the interval 5, 6, correct, to 2 decimal places. Now we have a formula for Newton-Raphson method. It's g of x, so Newton-Raphson method. So we can say x to the n plus 1 is equal to x subscript n, well, x subscript n plus 1 minus f, no, not f, minus, so we're using g, the context here, so g of x subscript n over g prime x subscript n. So we need g prime. Let me put g prime up here. So g prime is the derivative of g, which would be 3 cos 3x. Good. So we have x subscript 1 already, 5.5. All right. We also have x subscript 1, which is 5.5. So we need x subscript 2. X subscript 2 will be based on this formula. It will be x subscript 1 minus g of x subscript 1 over g prime of x subscript 1. So this becomes so x subscript 2 will be 5.5. That's minus g of 5.5 upon g prime of 5.5, and this would give me x subscript 2 5.5 minus, what was g of x was sine 3x, so sine 3 times 5.5, so sine 3 times 5.5 upon, and g prime is 3 cos, so 3 cos 3.5, so it's 3 cos 3 times 5.5, and you can use a calculator to do that. 3 times 5.5. Alright, let's use our calculator to do this calculation. Remember to put your calculator in the radian mode. So that's 16.5 the angle, so that would be 5.26 if I'm just working with 2 decimal places. Let's do another iteration. Let's do one more iteration. Let's do x subscript 3. So x subscript 3 will be x subscript 2 minus f of, well, not f, g minus g, so context, so the function is g, right? So g of x2 over g prime x2, so this would be equal to, so x subscript 3 would be equal to x subscript 2, which is 5.26 minus g of x2, so it will be sine 3 times 5.26 over 3 cos, so 3 times 5.26 over 3 cos 3 times 5.26. So both of them is 3x. Alright, and just pause and use my calculator. And I'm getting now 5.24. Notice the question, did it say how many iterations to use? The question did not say how many iterations to use, so 2 is usually enough. So let's continue. So we are now to question 4, and you will need to go to the next video for question 4.